Hello everyone, this is Chao Wang from Zhejiang University. The paper I will be presenting today is titled Wavesdropper-Through Word Detection of Human Speech via Commercial mmWave Devices. I will present the paper in the following aspects. Now let's start from the background. Voice communication can happen everywhere and anytime in our life, from face-to-face talking to online conversation. To guarantee the security of the speech during the communication, sound isolation, such as soundproof walls, is often taken to prevent sound waves from leaking out of the room. However, there are works revealing that the speech-related vibration can be used for eavesdropping. Typical methods include RF signals, motion sensors, video cameras, and LiDARs. We find that most of them focus on the machine-rendered speech, which is played by loudspeakers. So in this paper, we will change to another rarely studied topic, the security of human-rendered speech that is produced from human vocal organs. To recover human-rendered speech, recent work reveals that the vibration of human throat contains abundant information about the speech. A customized mmWave sensor is developed to capture the delicate throat vibration of the speaker by transmitting and receiving the mmWave signals. So based on this idea, in this paper, we want to ask a question, whether the vocal vibration of the speaker can be a side channel for confidential speech. More specifically, considering such a soundproof environment, where the speaker talks about something important, an adversary wants to know what the speaker talks about. Due to the soundproof protection, traditional methods to record the sound waves does not work anymore. To compromise the confidential information of the speech, an adversary chooses to use a mmWave sensor to penetrate the wall and transmit mmWave signals towards the room. If the attacker can extract the speaker's vocal vibration from the reflected mmWaves, then the confidential speech may be compromised. To investigate the above idea, we first performed a feasibility study to validate the relationship between the speech and the reflected mmWave signals. We used a mmWave probe to transmit signals towards the speaker's throat area. The sensing distance is about 2 meters in a line of sight condition, and the speaker said 0, 1, 2, 3 two times when we transmit and collect the mmWave signals. These are the results of the recorded audio and extracted vibration from reflected mmWaves. We can find that the audio and vocal vibration show a high correlation in the time domain, and the patterns of the same speech content shows a high similarity in the spectrogram. This indicates that we can differentiate speech contents only by the mmWave signals. As we have validated the relationship between the speech and extracted vibration from reflected mmWaves, we further ask a question, is it feasible to recover the speech from mmWave signals in the non-line of sight condition? So we performed another experiment in a non-line of sight condition by penetrating a wall to sense the human throat. The distance is set to 1 meter, and the speaker counts from 0 to 9. We plot the joint frequency and time domain, and we find that, compared with the line of sight condition, the power of reflected signals from human throat decreases a lot due to the blocking condition. To extract the delicate vocal vibration, we apply wavelet analysis on the extracted signals, and we find that the vocal vibration is still observable in spite of the non-line of sight condition. This indicates that sensing the vocal vibration from through-wall eavesdropping is possible. Although the feasibility study shows a promising future to achieve the through-wall attack, there are still some challenges to overcome. First, due to the blockage, the attacker has no prior knowledge about the room layout, which brings difficulties for the speaker localization. Second, there can be chairs and tables in the room. These objects can cause background clutters, which make it difficult to extract the delicate vibration. Third, the features of extracted vibration from mmWave signals is implicit, which means the attack results is not intelligible for human hearing, so speech recognition with high accuracy is required to translate the speech contents. To solve the above challenges, we develop an end-to-end attack system called Wavesdropper. The system can achieve through-word detection by sensing the speaker's throat vocal vibration and recognize the words with high accuracy to compromise the speech. When reflected mmWave signals are demodulated by the hardware, we can acquire the bit signals. Then we apply the fast Fourier transformation, also called range FFT, on the bit signals. The FFT results indicates the distance of the detected objects, and the amplitude changes indicates the vibration. To locate the speaker, we calculate the power density of each FFT point and select the one with the highest power density. Considering that the speaker may change his position during the speech, we further apply the speak tracking algorithm on the selected FFT point, and then we extract the amplitude values and apply the normalization to constrain the trace. The trace contains the vocal vibration. To mitigate the impact of clutters in the background, such as human motions, we apply the complete ensemble empirical mode decomposition algorithm on the extracted amplitude trace. The algorithm decomposes the trace into several components with different modes. Then the modes that contain clutters are filtered out by the threshold. The threshold is determined by the noise level of the trace. Finally, the remaining components are combined into a reconstructed signals. To extract the delicate vibration in the signals, we further apply the wavelet analysis, which decomposes the signals into an approximation part and detail parts. Considering the detail parts contain components with delicate movements, we can choose a specific detail part or combine several detail parts for signal reconstruction. The reconstructed signals mainly consist of the vocal vibration. Hereafter, we call it millivocal response. Next, the millivocal response is fed into a module for word-level segmentation. The segmentation is achieved by calculating the features of each segment and combines successive segments with feature values higher than specific thresholds. When we get the segments corresponding to single words, we feed them into a deep neural network for word inference. The next is the evaluation. We build a prototype based on a commercial mmWave probe and use a laptop for signal processing. The network for word inference is trained on a server with GPUs. We tested the system performance in a conference room with soundproof glasses. To train the neural network, we built a dataset containing 57 different words. The data is collected from 23 volunteers with over 50,000 samples in total. We use the top key accuracy and the defined millivocal signal-to-noise ratio as the metrics. Here is the overall performance of Wavesdropper. We find that the top-one accuracy for 57 word detection recognition can be over 91%, and there is no obvious bias for the confusion matrix. We'll also test the system under different distances and orientations of the speaker. We find that the system can achieve over 83% accuracy when the distance is less than 5 meters, and the millivocal signal-to-noise ratio is stable within 30 degrees. We also evaluate the system performance under different environments and with different background noise. We find that the system is resilient to the environment changes and also resistant to the acoustic noise in the background. To further investigate the attacker's ability, we performed the word recognition onto speakers with two separate probes. We found that the system works well and is extensible for multiple speaker eavesdropping. Here, we give two kinds of countermeasures to mitigate the attack. The first is to shield or jam the malicious mmWave signals. The second is to interfere the vocal vibration with another vibration source, such as a vibrating plate near the speaker's throat. Finally, we conclude the paper with the following aspects. We reveal a new speech threat of through-wall detection via commercial mmWave devices, and we proposed an end-to-end attack system which can recognize up to 57 words with high accuracy, and we also give the countermeasures to mitigate the attack. That's all. Thank you.